Now in this video we'll see how to find inverse Fourier transform of the given sequence. Along with that we'll see how to find Fourier transform of periodic functions also. Now let us take the first example as del omega. Now in order to find Fourier transform of this function, inverse Fourier transform, we can write I of t of this is equals to 1 upon, we have the formula as 2 pi integration, this is with respect to omega, x of j omega into e raised to plus j omega t into d omega. We'll put the value of given function, that is del omega. This exponential term will keep same into d omega. Now we know the property of del omega. Del omega will have an amplitude 1 only for the case when omega is 0, and its amplitude will be 0 if it is not equals to 0. So if it exists for a single value, there is no need of integrating it. So if I put it over here, I will get at omega 0 this will be e0, and we have another term omega here, so this becomes e raised to 0. Now del 0 is 1 and exponential 0 will be 1, therefore we'll get inverse Fourier transform of del omega is equals to 1 divided by 2 pi. So if I shift this 2 pi here and this Fourier inverse over here, I can make this term as Fourier inverse of 2 pi del omega will be equal to 1. Now if it is equals to 1, we will get one important relation from this, that is, if it is Fourier inverse, if I shift it towards RHS, it becomes Fourier transform. Therefore we can write Fourier transform of 1 will be 2 pi into del omega. Actually our answer is this much, but here we have taken one new term which is most important, as Fourier transform of 1 will be equals to 2 pi into del omega. Now if it is there, we'll see the next example which is related with the same. Here it is. I'm writing that example. X of j omega is equals to del of omega minus omega naught. Now in order to fetch its inverse Fourier transform, we can use a property that is called as frequency shifting property. If you remember this property, frequency shifting property, that simply says whenever there is a shift in the frequency domain, the same will replicate in the time domain, and it was given as e raised to j omega naught t into x of t's Fourier transform was equal to x of j omega minus omega naught. We have proved this property in earlier videos. Now I can make use of this one. We know that this is shifted by omega naught, so if I put it here, del of omega minus omega naught, which is equals to, I am treating this value as 1 and then I put it here. We have that relation. I can just show you over here. Here it is. Fourier inverse of del omega will be 1 by 2 pi. That means instead of x of t, we'll get this term as 1 upon 2 pi into this shifted by omega naught, so we'll get the same relation as e raised to j omega naught into t. Therefore we can write Fourier inverse of del omega minus omega naught will be equals to 1 by 2 pi into e raised to j omega naught t. Now this is the answer of given term. Now from this also we will get one more important relation. Here Fourier inverse, we will shift it over and 2 pi in this case, so I can write Fourier transform of exponential function, that is e raised to j omega naught t, becomes equals to 2 pi into del of omega minus omega naught. Now this is another important correlation that we can use in order to fetch Fourier transform of periodic function. Now let us take the example. Here I have written that example. Find the Fourier transform of x of t as sin omega naught t. Now friends, in the first introductory lecture we have seen Fourier transforms are used to represent non-periodic signal, but as far as sine and cosine are considered, they are periodic. So the question arises, how can you represent non-periodic function in terms of periodic function? So for that case, here I am representing x of t in terms of exponential function as e raised to j omega naught t minus e raised to minus j omega naught t divided by 2j. I am splitting this term as 1 upon 2j into exponential minus 1 upon 2j into exponential. Now in earlier example we have determined, here it is, the Fourier transform of exponential term will be 2 pi del omega minus omega naught. Now I am using the same relation over here and directly we will find Fourier transform of x of t becomes equals to 1 by 2j as it is. Now exponential ka Fourier transform is 2 pi del omega minus omega naught minus 1 by 2j into 2 pi del of, now this is minus term, so we'll get this as omega plus omega naught. This is an important term. In this case this is omega minus omega naught, this is omega plus omega naught. Now this two will get cancelled and we are left with pi by j del omega minus omega naught minus pi by j into del of omega plus omega naught. Now this will be the Fourier transform of sin omega naught t. We can make certain arrangement. I can multiply with j here, so this will be j pi j square and this term. That are the part that are left with us. Similarly, if you take one more example, that is for cos x of t as cos omega naught t. Let us represent this again in terms of exponential terms as e raised to j omega naught t plus e raised to minus j omega naught t, this entirely divided by 2. Split the terms, 1 by 2 exponential plus 1 by 2 exponential. Now we know the exponential's Fourier transform as 1 by 2 into 2 pi del omega minus omega naught plus 1 by 2 into 2 pi del of omega plus omega naught. This two will get cancelled and we are left with pi del omega minus omega naught plus pi del omega plus omega naught. In this way we can find even Fourier transform of periodic function. I hope you understood these examples also. Thank you very much.